EDX Decision 1, Graphs and Networks 1, Definitions and Spanning Trees. Minimum spanning tree using Prim's algorithm. The spanning tree is a graph that connects all the nodes but has no cycles, loops or repeated edges. If we have a graph, we can select a subgraph that is a spanning tree. There may be more than one possible tree. So for example, here we have a graph, and possible spanning trees look like that. And there are other examples. And you'll notice there are no cycles or loops or repeated edges in each of these spanning trees. So the question is, how can we find a spanning tree with a minimum total without looking at all the different possibilities? Prim's algorithm was actually developed in the 1930s, but later republished by computer scientist Robert Prim in 1957. It has applications to things like gas supplies, water supplies, mobile network signals, where you only need one access to the supply without having multiple access points. Select any node. Select the shortest edge connected to that node. Select the shortest edge connected to any node already connected, and repeat step 3 until all nodes have been connected. Remember to check all the nodes you have already connected during the process. So for example here, I'm going to start by selecting node S. I now look for the shortest edge connected to this node, which is the 11. So I've connected S to R, and keep a list of the edges as you're going along. I now look for the shortest edge that I can connect to either of these two nodes, and the shortest one I can see is one of the 12. So I'm going to choose this 12 here. I could have chosen the other one, and it doesn't matter which one you choose. I now look at the next shortest edge that I can connect to S or C or R. And the next shortest one is the 7. So I've done SR, SC, and I've now connected CL. So now look for the next closest node to R or S or C or L, and it's this 5 here. So that's WL. So we had an 11, a 12, a 7 or a 5. So the minimum spanning tree is 23, 35 units long. That solution isn't unique. For example, I could have used the other 12 instead of that 12, but it will be an optimum solution. What happens if you start at a different vertex? You will still get an optimum solution, but it may not be the same solution that you found previously. What happens if more than one edge can be chosen? Doesn't matter which of the two edges you choose, you will still get an optimum solution, but it may not be unique. So here I'm going to start with node A, and we'll see what happens. So the shortest edge I can connect to A is 30. So that's A, C at 30. The shortest edge I can connect to A or C is the 22. So that's CD at 22. The shortest edge I can connect to A or C or D Well, there's a 24, there's an 18 and a 24. The shortest one is going to be that 18. So that's D, E, at 18. The next shortest edge I can connect to A or C or D or E. So there's a 29, a 28, a 26, a 34, a 31, a 24. So the next shortest one is that 24 there. So that's BD at 24. The next shortest connector I can connect to the current solution is 34, 38, 26, 28, 29. So the next shortest one is 26. So that's EG at 26. The next shortest one I can connect, well, as I can see, a 21, and then then 21 is the shortest. I'm going to connect that 21. So that's FG at 21, and the next shortest connection is this 33. So I can connect H to G at 33. And the total, the minimum spanning tree for this one is 174. The minimum spanning tree, 174 units. And you'll notice solution doesn't have any repeated edges and definitely no cycles. Some of the common errors with Prim's algorithm: not starting at the specific node that was requested in the question is a common mistake. Not choosing the shortest edge to add to the current solution. Forming a cycle by accident, and it's worth noting that if you apply Prim's algorithm correctly, it should never be possible to produce a cycle. Not looking at all the connected nodes when looking for the next edge. Forgetting to record the order of the edges as you're going along, and forgetting to state the length or the weight of the minimum spanning tree at the end. In the next session, we'll be looking at minimum spanning trees, applying Prim's algorithm in tabular form.